What I'm presenting today is some work that we undertook with the Institution of Civil Engineers as part of their National Needs Assessment, and it's looking at building pathways to Paris. Some of the stuff I'm going to cover, Mike has already presented on, so I'll probably skip a few slides and get to some of the more meaty stuff. But basically, quick look at the UK's climate change targets, the modelling that we've been involved in at Oxford with this Infrastructure Transitions Research Consortium, looking at a couple of the details of an alternative pathway to reducing emissions, and then something about getting the energy mix right. So the UK has the Climate Change Act. I think it's one of the few countries on earth that has a legally binding requirement on reducing emissions. I'm both English and Australian, and my country back in Australia is one of the only developing countries that has gone backwards in its emissions reductions. So the part of me is very happy to be English. Also, you're beating us in the rugby too, so I can go that way in that regard as well now. What we've got here is the Climate Change Act requirements, 80% reduction by 2050 from the 1990 levels. The UK has been doing rather well in regards to their emission reductions. A lot of that is low-lying fruit, and a lot of it's in the energy sector in terms of efficiency, the RAP program in waste management and so forth. Some people say the Kyoto Protocol never worked, but it seems to have worked for the UK. They did a good job of meeting that requirement. Here are the carbon budgets here. You might wonder where we are in terms of the Paris Agreement. So the UK joined as part of the EU Paris Agreement, and the EU Paris Agreement was for a 40% reduction. So the requirements by the Climate Change Act are actually better than what the EU signed up in terms of their pledge for the Paris Agreement. Where do we have to be to meet 1.5 degrees? We have to reduce our emissions to nothing by 2030. Because it's a cumulative amount of CO2 in the atmosphere, so it's the area under this graph that we have to reduce. So people are talking about overshooting, and if I had time I'll talk a little bit about the problems with overshooting and negative emissions technology, but basically that's the picture we're looking at. What does that mean for infrastructure? Well, it means a lot. Even with 1.5 degrees, there's a lot of adaptation that needs to take place, particularly in terms of flood damage mitigation, adaptation in the UK, but also mitigation pathways are essential and must be planned, I'm going to argue, in order to minimise costs. You can see there in terms of, this is a bit of an old graph, but in terms of the requirements for reducing emissions, most of that has to do with infrastructure. The energy sector is a big component of it, but also transport, supplies to industry, building sector. Agriculture is a bit of a difficult one. There are things that they can do. Probably one of the best things you can do is eat less meat, but I'm not going to talk about that. I'm going to be talking about the infrastructure. And the work that we did as part of this Infrastructure Transitions Research Consortium, it's a consortium of 7 leading universities in the UK led by University of Oxford, where I work. We have had the good fortune of working with a number of different collaborators through the last 5 years. It's been going since 2011, and more recently with the Institution of Civil Engineers, which is the basis of this talk, the Committee of Climate Change and the National Infrastructure Commission. The idea of Infrastructure Research Transitions Consortium, ITRC, is that it was developing new models to look at these national scale pathways and designing national infrastructure. We built a model. That was a big part of the work that I was doing, is bringing this, what I lovingly called the beast, together. We've got different sector models: energy, water, transport, digital communications. It's called a system of systems because each one of these is a system in its own right. So there's an energy model that's geospatially disaggregated, and then it is also linked up with other models like transport and water. We look at the interdependencies and so forth. That's a complex model, but the methodology is fairly simple. We run scenarios through this system, different population, economic growth, climate change, and then we look at different strategies for meeting those different scenarios of uncertainty. And then we look at how well each of those perform based on several metrics, cost, carbon emissions and so forth. And so it was around the cost and carbon emissions that this piece of work was done. There's a database underneath it all and a whole lot of visualization, but I won't go into that detail. But in terms of the model, it is unique. One of the reasons why we were a part of the National Needs Assessment and also working now with the National Infrastructure Commission is because we were the only ones that had this model. And one of the key things that we have is a set of socio-economic and climate scenarios that are consistent between all the different models. A bit of the frustration that the Commission has at the moment with working with the individual ministries is they all have their own models and they all run their own different population economic scenarios, and so it's very hard to look at across all the different sectors. We can do that for them. We can also look at the interdependencies between the different sectors. So a lot of the energy requirement, as Mike said, is from transport. A lot of, you've got to take into account the water for cooling in terms of your water systems, for energy generation, and digital communications is really the X factor. It can change everything with Internet of Things, smart metering, remote sensing and so forth. So in terms of the modelling, we've modelled demands very similar to what Mike presented. You see here 2015, the levels of electricity supply and demand by the different sectors. This is high, central and low population scenarios for one particular strategy with unconstrained demand and another particular strategy with demand management, so you can see a big reduction. And that's one of the biggest differences you've seen between these two is that demand reduction. This is the gas sector. You can also see some massive differences in the gas sector, and I'll get to that. So one of the most important components of our modelling work is that demand management, and that's what helps us with existing technology meet the Climate Change Act. This number isn't the same as what you saw in the other graph. Because we don't model all emissions in this system, we work with the Committee on Climate Change to work out how much we have to reduce infrastructure's emissions in order to meet the Climate Change Act. And also infrastructure has to do more than other sectors because agriculture and so forth are not expected to be able to do as much. Transport, aviation, to some extent. So this is that unconstrained demand. This is the demand management strategy. It's not a straight line, Mike. We've got a bump in ours. That's actually the Hinkley plant, I believe. But I'll just go into the details of what that actually means in terms of the pathway. So as I said, one of the key components is demand management. In short term, improved insulation, and there's some fantastic technology I'm seeing here at this event. LEDs lighting is a big deal because you have to do something about those periods where load ramps up away from the renewables, and LEDs and lighting standards can do a lot with that. Long-term solutions are more the smart meterings, and also you're looking at a situation that's a bit more long-term because you've got to wait for those Internet of Things products to come out so that your washing machine can get a signal from the market about when the price is cheapest for it to run. So that's going to take some time for those products to get into people's households. This is energy demand through time, that we keep the peak demand consistent. We don't actually have a lot of information about what will happen here. Technology is going to play a huge part. What is it after LEDs? Is it bioluminescent wallpaper? Who knows? But we are doing some work now with the National Infrastructure Commission about trying to parameterise and understand some of the impacts that technology can have. In some cases, technology can actually increase demand, not necessarily reduce it. So there's some nuances to that analysis. Electrification of transport, we have it ramping up a fair bit. Electric cars, it's an interesting scenario. I believe Volkswagen has recently announced that they're not going to expect to make a profit within the next decade because they're investing so much in electric cars. As you'll see a bit further down the track, there is a bit of a problem for that because at the moment, because we don't have low carbon electricity, well, not as low carbon as we need it, someone driving an electric car is actually producing more CO2 emissions than someone driving a petrol car. Petrol is actually quite efficient. But we still need early adopters and we need to move the industry in that direction if we're going to decarbonise. So thank you to those people that are taking that burden on themselves. As I said earlier, as well. Aircraft and shipping is going to be quite difficult. Electrification of heat. My colleague in Oxford, Nick Ayres, spent a whole hour just on this one subject. It's one of the biggest issues in terms of decarbonising the energy sector, so I won't be able to go into a lot of detail. Some of the key points is its peak happens at the same time as our electricity peak at the moment, and it's about it can be up to 4 times as high. So if you convert that electricity, that makes your peak even higher, much higher. So that's something you need to take into account. Also, in terms of heat pumps, they are the way of the future when you decarbonise, but at the moment we're about here, and that black line is the emissions from heat pumps. You're above a gas burner at the moment because your electricity is not decarbonised. But so if we're here now and we're not going to be here until another decade or two, what do? Do you put in heat pumps or not? So my point is we need to be planning this stuff. We need to be looking at these transitions. Also, hydrogen is a possibility for retrofitting the existing gas work, and I'll show you why that is important a little bit later. Carbon capture and storage, it exists, it's a current technology. The Norwegians are doing a fair bit of it. There's existing plants in America and Canada. So it's currently operating. They assure us that it's safe and they can bury it far enough down that it won't ever come out, even if there are earthquakes. But it is a bit of an unknown, I must say, and it is quite expensive at this point. Not just in terms of money, but also some of the work that one of my colleagues, Jim Hall, did with a student is looking at if you have carbon capture and storage in your energy system, you actually need more energy to pump the gas down into the ground. Because you need more energy, you also need more water. So in times of drought, in places where we've got a lot of these big fossil fuel plants, you're going to run into some trouble in terms of water demands. That gives you an idea about why we do those integration between the different sectors in our modelling. Renewables and nuclear. I personally don't have a big problem with Hinkley Point C. I'm going to put that out there right now. Because we need dispatch energy to solve some of the problems with renewables, and I will talk about that a bit later in terms of the energy mix. But in terms of renewables, we do conceivably have enough energy to meet the demands by 2050. It'll require us taking up a lot of the North Sea and offshore wind, as Mike said. Also, a fair bit of space on the ground in terms of solar. And tidal is a fantastic option, but I won't go into too much detail there. Michael's already done some of that detail. So at the end of the modelling, you have this transition through to 2050. Similar to what Mike showed in terms of, I'm actually very pleased to see how similar it is to what Mike has showed. One key point is keeping that peak level very similar. One interesting point here to note in the gas sector, these are the two strategies. The demand management strategy, because you're electrifying heat, you're actually reducing your gas demand by quite a lot. The gas network is actually bigger than the electricity network and supplies more energy. So there's a big question mark over what to do with that gas network. One of the projects happening in Leeds at the moment is to retrofit that for hydrogen, but that's in experimental phase at the moment. Now on to the right energy mix. This is, to me, this happened in October 5th last year, it looks like a picture out of a Michael Bay Transformer film or something like that. That's a cyclone. They're usually called tropical cyclones. The tropics are up there. So that to me, I mean, it's a 1 in 50 year event, they say, but for me that's quite striking. What happened was this cyclone came through, hit South Australia. They were getting up to about 40% of their energy from wind at the time because the turbines were flying like crazy until they got to the point where the winds were going too strong. Up to 100 kilometres an hour, the wind power had to switch off, and so a much bigger load came from an interconnector with Victoria, which was using a brown coal power plant. The winds then knocked down a couple of high voltage transmission lines, overloaded the interconnector, then all of a sudden the whole state's in blackout. The now Prime Minister of Australia, it's hard to keep up, I realise that, got into a bit of trouble for blaming renewables for this. and he copped quite a bit of flack from the renewable energy sector, but he did have a point to some degree, that you do actually need that energy mix in order to deal with situations like that. It doesn't really matter in terms of our modelling from what we've seen in terms of how you do that energy mix. The previous Australian Prime Minister, it's hard to keep up, I know, once said that coal is good for humanity. He got that wrong, obviously, but the only thing he really got wrong was the tense. Coal was good for humanity, it's not anymore. And so in all of our modelling, we phase out coal. But what you see the difference between these two strategies, they have the same cost, the same outcome in terms of emissions. This one has more nuclear, this one has more gas turbine with carbon capture and storage. It doesn't really matter a lot to our modelling which one you choose, so that's up to what you believe is the best bet, really. Another point, teaching the duck to fly. This is an interesting, now famous graph that's come out of, that's from a Californian grid operator. The top curve is the load on the system by consumers demanding electricity. The bottom of it is the ever-increasing amount that's taken away from that, the load operators by renewables, by solar in particular. So solar's taking more of that load away from them, and the head of the duck is getting higher because there's more people, more demand in that peak period, where solar doesn't do anything for you. So they called that the duck graph, and then someone came along and said, well, that's a duck sitting in water. A duck flying is much more streamlined, and that's what we need to do. We need to teach the duck to fly. So we need various technologies and strategies in order to reduce that situation there. On a national scale, which is where we do our modelling, some of the key points are putting in renewables, for instance, strategically, so they give you the power when you need it, not necessarily when you're maximising profit. A lot of the situation at the moment is people are putting wind turbines when it maximises profit, but that's not necessarily where you need the energy the most. So you need the bigger picture. Also getting people like the water industry, wastewater industry, to do a lot of their demand at off-peak hours and so forth. It's a very good article if you have the time to have a look into that. One last point in terms of the work that we did in terms of coordinating the pathways. These are two versions of that unconstrained demand model. The only difference is I delayed the nuclear reactors, but I could have delayed an alternative renewables, but it was easy to do. There's only 3 of them in the pipeline. So you delay those by 10 years, which I'm reliably informed is quite possible. That has an impact in terms of emissions of around 400 megatons of CO2. So that's about over a year's worth of emissions from the UK. That comes about because electrification of heat and transport is going up all the time, and it's pretty hard to stop it, particularly transport. So if you don't decarbonise the energy sector early enough, you actually create more emissions from the electrification. So in conclusion, may you be born in interesting times. You definitely are in interesting times. There's a lot of work that we need to get done. I think it's very important that we get the energy mix right if we are going to meet what they're calling the energy trilemma, keeping it energy affordable, sustainable and reliable. And I believe that national planning, and I hope I've shown that, and coordination is essential to that. We wrote a paper on this that a lot of this work came from. We also help with the national needs assessment if you have more questions apart from what you hear today. Thank you.